Hey everyone, welcome back to the channel. Today we're diving headfirst into one of the universe's biggest, baddest mysteries, black holes. Specifically, we're talking about the singularity, that point of no return right at the very center. Sounds intense, right? Don't worry, we're going to break it down so it makes perfect sense. So what even is a black hole? Imagine a star way more massive than our sun running out of fuel. When that happens, it can collapse under its own incredible weight. Think of it like squishing a giant sponge into a tiny, tiny pebble. All that mass gets packed into an infinitesimally small space. This creates a gravitational pull so strong that nothing, not even light, can escape once it crosses a certain boundary. That boundary is called the event horizon. It's like the universe's ultimate one-way door. Once you cross that event horizon, you're on a one-way trip to the center. And that center is the singularity. Now here's where things get really wild. According to Einstein's theory of general relativity, a singularity is a point of infinite density. All the matter that made up that giant star, and everything else that has fallen into the black hole, is crushed into a single, one-dimensional point. Let that sink in. Infinite density. It's a concept that breaks our everyday understanding of physics. Imagine taking Mount Everest and squishing it down to the size of a grain of sand. Now, imagine taking the entire Earth and doing the same. Now, imagine taking a star millions of times bigger than our sun and crushing it into a point with zero volume. That's the kind of mind-bending reality we're dealing with. At the singularity, the laws of physics as we know them, including gravity and spacetime, completely break down. Spacetime, which you can think of as the fabric of the universe, becomes infinitely curved. It's like stretching a trampoline so much that it just rips a hole in the middle. Time and space literally cease to exist as we understand them. For an object falling in, time would stretch out to infinity from an outside observer's perspective. But for the object itself, its journey to the singularity would be finite and, well, final. So, what would it be like to actually approach a singularity? Let's just say, it's not a vacation spot. As you got closer, the gravitational pull would be so uneven that it would stretch your body apart in a process scientists poetically call spaghettification. The gravity pulling on your feet would be so much stronger than the gravity pulling on your head that you'd be stretched into a long, thin strand of atoms. Not exactly a pleasant experience. Now you might be thinking, hold on, if the laws of physics break down, how can we even talk about this? And that's the billion-dollar question. This is where Einstein's theory of general relativity meets its limit. General relativity is fantastic for describing gravity on a large scale, like planets orbiting stars. But for the super-small subatomic world, we have another theory, quantum mechanics. The problem is, these two pillar theories of modern physics don't play well together. They give different answers when you try to describe the same thing, especially in extreme environments like a black hole singularity. This is one of the biggest challenges in physics today, finding a theory of everything, or quantum gravity, that can unite them. Scientists are working on theories like string theory and loop quantum gravity to try and solve this puzzle. String theory suggests that at the tiniest level, everything is made of vibrating strings of energy. In this view, a singularity might not be an infinitely dense point, but rather a super-dense fuzzball of these strings. Loop quantum gravity proposes that space-time itself is made of tiny, indivisible chunks. In this model, you can't crush matter down to an infinite point because there's a smallest possible unit of space. The collapse would halt, creating something incredibly dense but not infinite, sometimes called a Planck star. These are just theories, of course. We can't go and poke a singularity to see what it's really like. The event horizon conveniently hides it from our view, which is what physicist Roger Penrose called the cosmic censorship hypothesis. It's as if the universe is protecting us from seeing the place where its own rules fall apart. But we can study the effects of black holes on their surroundings. By observing stars orbiting them and detecting the gravitational waves created when black holes merge, we can gather clues that help refine our theories. So, to recap, a black hole forms from a collapsed massive star. At its heart lies the singularity, a point where matter is so compressed that our current laws of physics break down. It's a place of infinite density and infinitely curved spacetime, hidden from us by the event horizon. Trying to understand it is pushing the boundaries of human knowledge, forcing us to search for a new theory that can explain both the very large and the very small. It's a humbling reminder that no matter how much we learn about the cosmos, there are still fundamental mysteries waiting to be solved. The singularity isn't just a physical object. It's a signpost pointing toward the next great revolution in physics. It's the ultimate here be dragons on the map of our universe. Thanks so much for joining me on this journey into the heart of a black hole. It's a complex topic, but hopefully, this made it a little clearer. If you enjoyed this deep dive and want to explore more cosmic mysteries, make sure to hit that like button, subscribe to the channel, and ring the notification bell so you don't miss our next adventure. Let me know in the comments what you want to explore next. See you in the next video.